Okay, so I also shared my screen. So please, your name is Matteo. So Matteo, please go on.
Yeah, okay. Thank you for the opportunity. I was just going. I don't know if it's the best case to just say it now or at the end of the class. But if it's good for you now, I'll go now. I mean,
it's your preference. If you at the end of the class, maybe that few students are here. But
yeah, true.
But if you prefer at the end, it's fine to me. It's not.
No. It's just because it's like an overview of the course, because we also taught in person. I don't know if you reminded me, but yeah.
Yeah, please.
Okay, so yeah, I was just I'd like to say that in general the course was very interesting to me, and also the singular topics that were chosen seem very well presented. However, since the first introductory classes, as I already told you, I felt a bit of discomfort on how those topics were framed. So I am a bit critical here. Because namely, while I agree that with introducing the whole spectrum of science, I felt that a continuous focus on uncertainty in data and models were some kind of unnecessarily stressed. And I say this because there is this known effect that can be triggered psychologically, which is also called and defined as soft or implicatory climate change denial, which is defined as an implicit form of denial where the facts are recognized, so the whole science of climate change is recognized, but without any consequent responsibility to act on them. And so this enables people to avoid feeling disturbed and so responsible for their actions. This can happen because when you over focus on uncertainty and adding frequent expression of probability, there is this psychological trigger to face such a great challenge, I think, by science and humanity as a whole. And also there is the risk of intellectualization, which is relevant in a university class, as it's about engaging with climate change, but in a primarily academic context. And this makes the issue like an abstraction. And so it lacks of the stimulus to prompt people to take concrete actions. So as I said, I already expressed these concerns of mine directly to Professor Montanari. And yeah, Professor, I mean, you seem very well available to discuss and eventually implement this feedback into the next classes. And I appreciate it a lot. And that's why I'm like trying to provide this feedback now. And also we acknowledge that the students joining the course explicitly comes from very different backgrounds. I'm from archaeology, but I know there are also medicine students. But because of this, I was fearing that the choice to present very specific topics and the technical solutions in deep may have ended up highlighting only the hard science, the STEM side of this emergency. And this will kind of lack of the social sciences and the civil way on how to engage with climate action, and can bring to further disavowal of disengagement by students. So this may end making the problem like feel distant or of concerns only of a certain niche of scientists and technicians, and not to any other academic or citizen with other intellectual backgrounds, such as the other students. I felt this also. Thus, the effect ultimately risks to be that of disengaging the majority of attending students from the actual possible highways of actions, and particularly those attending whose field of study is even slightly away from the research is presented. So to kind of sum up, now that we went through all of the classes and lectures, considering all that I've said, I have still this feeling that the whole course kind of fell short on dealing with these kind of issues. Because in the end, we've got a quick reminder of the anthropogenic causes of climate change, at least in the class after I provided this feedback. But like I also have not seen the references to the just maybe due to humans on the slide modified till now, but I'm of course confident that's not intentional, and that's not what I want to say. Also, I understand that it's difficult to adapt a course and its material while classes are ongoing. And so I'd rather recognize that the major issue lies in how the course is structured, maybe, and this is only partially due to the professor in charge of it, while the responsibility for me like falls more on the institutional level. Mainly, it seems that the course was based on the idea that people just presented with data will take actions by just knowing. But this is a way of communicating science and advocating for change, for climate action in climate policies and social behaviors, which didn't work since the establishment of various organizations and research groups internationally. And we had the conferences of party with resonance of the data, but not on the actual way of actions of citizens. So the point is, if the aim of Unibo in delivering this course truly was to make students aware of the emergency and inform them into actions, because I also see in the outline of the course the SDG goals mentioned. So whatever their different field of studies, the one of the attendee students were, as expected from a soft skill class, it should have had to be consistently structured in the program, also taking into account those attending. So in the end, I'm afraid that, put it simply, this lack of seriousness on how Unibo decided to deliver the course shows yet a kind of another phase of greenwashing. And by this, I mean providing a course which appears to deal with this emergency only by name, which is useful only to be added into curricula, while trying to cover up like a lack of consistency into a consistent program in climate action into education. And such a practice, either deriving from active interest or passive disinterest, I'm not advocating for that. Anyway, I thought it has to be spoken out and should have no room in an institution with similar resonance and responsibility, since it actually forms the last lines of actions to face the greatest challenge for the future of humanity as of now. So that's what I wanted to say, and I thank everyone for the attention. I just hope that this feedback can be useful to at least someone and also help to better deliver the course in the future.
Okay, thank you very much. There are some comments. I just would like to invite you to be short, because otherwise we take too much time for this discussion. But are there comments from the audience? Okay. Okay. Okay, this is fine. Okay, if you have any comments later, feel free to continue this discussion. Okay, so I give a very short reply because I don't want to take much time. So when we decided how to structure this course, we decided to call it Science of Climate Change, to make it clear that the purpose of the course is to discuss the science behind it. It's not a course on communication. It's not a course on psychology. It's not a course on sociology. So basically, this is the essential premise. It's a course on science. And as such, the professors, including me, were invited to teach on the scientific knowledge behind climate change. So you know that there are a lot of papers on the uncertainty of climate models, and this is a recognized challenge that science has to overcome precisely for reaching the purpose that you are advocating in order to be effective in convincing people, whatever. But let me talk about science. In order to be effective in setting the scientific basis for climate change, this is one of the biggest challenges. There are several research projects all over the world ongoing. So this is why I myself, but also I guess from what you said, also the other colleagues, I think you attended all the lectures, we are committed to teach you the uncertainty behind science now, because I think this is essential. It's an essential knowledge for you if you want to be able in the future to address the problem. And so I think this may, in a way, I'm not sure this is a satisfactory reply to you, but this in a way may explain what is our attitude. You know that we are all committed to contribute to solving this problem. One final thing, uncertainty shouldn't be seen as a limitation of science. Again, I'm talking about science. I'm not an expert in communication. So uncertainty is not a limitation of science. Science is by definition uncertain. And therefore, uncertainty is an attribute of information. If we neglect an attribute of information in science, we undermine the scientific progress. Finally, let me say one thing. I really appreciate your attitude, your constructive attitude, but there were some words that were a little bit like lack of serious approach by the university in setting. So serious means that in a way there is an implication that the university was not serious, was incoherent, as you said. I think that the discussion should keep a respectful tone. I'm not, I don't dare to say that you are not serious. I even don't think it. So if we really want that a discussion is efficient, is constructive, we should respect each other. But this is not related to the main question. The main question is about science. I hope that we can close this discussion because we took already much time. But if you want to give a brief reply to me, please feel free.
Yes, no, first of all, thank you for the reply. And I just can quickly say that I didn't mean to be unrespectful. I was just stating that, as I said, it's about structure. It's not lack of seriousness, but it's like providing a soft skills course. As I said, of course, it's focused on science, but then it should be restructured or not offered in soft skills, given the broader backgrounds that students that want to attend it may have. So that's what I meant. I'm not, of course, saying that it should not be focused on science, and I was not saying that uncertainty should not be taken into account. But since this is because itself has no flaws by itself, but providing it in the way it was and inside the like study plans in this way may just fall short on those aims that university, I hope, has. So it's that's just what I actually meant.
Yes, you know, it's again, the intention was to give a course on science, and the name, I think, is clear enough. And maybe that, I don't know, somebody else may give another soft skills course on science communication, maybe. But this one is related to science. I just want to say one final thing. I think I never put any doubt on the anthropogenic influence on climate change. I don't think I never downplayed the importance of the topic, because I think I always said that this is one of the greatest challenges for humanities. I mean, I just said that we have to be careful, especially when we go to devising strategies of the uncertainties. And when I say this in a conservatory way. So very often, when I give my consultancy to administrations, I take predictions that are worse than those by climate models, just because I want to take uncertainty into account. Because actually, sometimes when I take climate models and I look at the predictions in terms of water, in terms of hazards, they are underestimating the prediction. So don't assume from a scientific point of view that taking uncertainty into account means discarding a problem. You are talking about uncertainty in a pedagogic way. So if an opinion is uncertain, then I agree that communication becomes less useful. But if the scientific basis is uncertain, this may be an opportunity to strengthen the message and say, even there is uncertainty, but even if there is uncertainty, if I take the best prediction, I see that there are problems. So, I mean, uncertainty is something, as I said, something positive that should be taken as an opportunity. But one thing is uncertainty in data in science, and another thing is uncertainty in personal opinions. This, we shouldn't make a confusion on that. Okay.
Thank you very much. Yes.
And if you, anyway, if you change your mind about recording, etc., just let me know, okay? Otherwise, no problem in keeping it. Okay, very good. Thanks. And let's move forward. Any other question from the attending students related to exams or whatever before I start? Okay, very good. Now let me go to the last lecture. Unfortunately, this is the last one. Design of climate change adaptation actions. So the last lecture focuses on adaptation. And first, let me open the PowerPoint. There is a PowerPoint in the bottom, and let me open it. Okay, perfect. So I think you got an idea also from the lectures of other professors, what is climate change mitigation and what is climate change adaptation. And there is a fundamental difference, as you know. Mitigation is that we try to mitigate climate change or eliminate it. And the mitigation typically implies that we remove the causes of climate change. This means that, in particular, we have to reduce the CO2 emissions. This is mitigation. Mitigation is, as we will see, requires a global approach and a long time scale. Adaptation is, in a way, a less satisfactory approach because it takes climate change as a reality now, as an emergency, and tries to adapt to it. Therefore, it's not resolving climate change, but is trying to set the conditions to better cope with climate change. So in a way, as I said, it may look like a second priority because it doesn't solve the problem. And on the other hand, it has some advantages, as we will see in the next slide. I decided to start with renewable energy, with two pictures focusing on renewable energy, because as you know, the use of renewable energy is a possible strategy to mitigate the effect of climate change. And it's something that is very topical today. And let's see what is climate change adaptation with more details. So this is taken from Wikipedia. Climate change adaptation is the process of adjusting to current or expected climate change and its effect. It's one of the ways to respond to climate change, along with climate change mitigation. Let me say already now, these are not alternative. We shouldn't choose one or the other. We should know both. And then, depending on the problem at hand, depending on the context, we may integrate them or we may prefer one over the other. It depends, as I said, on the boundary conditions, and also, unfortunately, it depends on the resources that we have. Because, of course, these actions require resources and they have an impact on the economy. Okay, so let's.
Sorry, Professor, we can't see the slides from Zoom.
Oh, yeah, sorry. Why is that? Let me see. Because I forgot to sorry, because I shared the screen to open the discussion. Now you should see it. Okay, so now basically, what is the aim of adaptation? Is to moderate or avoid harm, is to exploit opportunities of natural systems, and for instance, to reduce the risk of floods or droughts, not the risk, to reduce, yeah, the risk indeed, to reduce the impact. Probably it's better understandable if I say the impact. I could also say to reduce the risk, but we will get into the details of what is risk later on today. Now, in the figure, basically, you see a list of the risks which are caused by an hazard. An hazard is, you can interpret the hazard as the probability, the likelihood of getting one of the disasters that are listed there, which are technological, for instance, and accidental disasters, such as oil spills. Another hazard is a natural hazard, such as a weather-related hazard. And there might be other hazards that are not strictly connected to climate change. But if we go to the second row, the brown one, the light brown one, weather-related disasters, these are all connected to climate change. Tropical cyclones, drought, wildfires, floods, severe storms, winter storms, and the hazard is the probability of getting these extreme events, okay? And this is a first important definition. What is the hazard of a given threat? It's the probability of getting this kind of event. Now, the probability is expected to be, let's say, increased after climate change. So the probability of getting a drought is expected to increase after climate change. So the probability of floods, the probability of wildfires, etc. Perfect. Now, mitigation tends to reduce the hazard, tends to reduce this probability. Adaptation means to reduce the impact. So the event happens with increased frequency, but the impact is decreased. Let me give you a very stupid example. Risk of flooding, I build a levee, and I have the feeling that even if a flood comes with a higher levee, higher embankment of the river, I decrease the probability that there is an overspill in the surrounding areas. So this is an adaptation. Now, adaptation and mitigation, basically they build resilience. They build the capacity for a community to absorb or recover or avoid a disaster. Now, let's see. I'm sorry, I had an expanded figure, I forgot it. So I forced your eyes to read very, very small font, which was not needed. Okay, so adaptation means to modify the socioeconomic and environmental systems to make them more resilient with respect to current and future climate forcing and with respect to their impact. Okay, now let me make a premise already now. I go forward in this slide and then I will come back. So compared to climate mitigation, adaptation generally operates at local spatial scale. So when I made the example of the levee, it's operating at local scale. Mitigation is more extended in space. And as you know, when we talk about reduction of emissions, this is a global strategy, requires a global approach. So in a way, if we want, adaptation is easier. Adaptation, on the other hand, is a responsibility of local administrations. So sometimes there is the risk that in a way, adaptation measures are discarded because local administration don't want to take the responsibility, and therefore they prefer to defer the responsibility to the higher levels. And this may cause an underestimation of the opportunities related to adaptation, because there are some adaptation measures that are not costly. We will see a list of possible measures are not costly. They could easily be done, but because they are a responsibility of the local administration, and the local administration have less resources, also in terms of planning, than higher level administration, sometimes there is the risk that the opportunities given by adaptation are underestimated. Another important consideration is the time scale. Mitigation requires a longer time scale. Even if we stop the emissions now, even if we were able, which is impossible, to stop human emissions completely, to put them to zero now, the effect on the climate will be seen much later on. And it's not clear when we talk about the time scale, what is actually the recovery time scale of the climate system, but we suspect that it's very long. And the time scale of adaptation is clearly shorter, because once that we build the levee, it's immediately in operation, and therefore, you know, this integration of the two strategies may be a winning action, because we may couple long-term solutions with short-term solutions, which is, of course, something that would allow to see the benefits immediately and to push the benefits into the future. Conversely, if we only rely on adaptation, you know, we may get an immediate benefit, but then if climate change keeps increasing and increasing, of course, we need in the future more adaptation, which means that it's not a long-lasting solution. Okay, and another important premise is that adaptation, it has been clearly understood and demonstrated, does not only depend on governments. I said just a couple of minutes ago, the responsibility of the administration, I mentioned it, but actually a successful adaptation should rely on an effective involvement of stakeholders, because, and also on the development of scientific knowledge, which is essential to engage with stakeholders. And so this is these are the premises from which I want to start. Let me now go back. Adaptation is very often involves engineering. I would say the vast majority of the adaptation actions involve engineering, while mitigation, it's an interdisciplinary effort. It may involve some engineering, but it also requires, mitigation requires the involvement with priority with respect to engineering of social sciences, and in particular economics, and also the involvement of communication science, the involvement of climate science, and etc. Another classical example of adaptation is building of reservoirs. For instance, here you have a picture of the Ridracoli Dam that was built in the Apennine of the Romagna region, close by here. By the way, if you get an opportunity to make a trip there, it's a nice place, and they organize visits. It's extremely interesting to know the story of this dam, which was built in the 80s, so it's only 40 years old, and it was inaugurated, if I'm not wrong, at the end of the 80s, so it's not a long time since it's operational. And what was the reason why they decided to build it? Apart from the availability of a nice location, nice means that was a location lending itself very easily to the construction of a dam, with the opportunity, with a low landscape impact, a low impact on on the tourism allowed to store a consistent amount of water. And the reason why this dam was built was that with the increase of tourism on the coastline of the Adriatic Sea, we had an increase of water demands. Increased water demand from groundwater associated to sea level rise caused saltwater intrusion. And there is a concurrency of these two factors. So the sea level rise is an important driver of saltwater intrusion. What does it mean, saltwater intrusion? It means that the saltwater from the sea intrudes into the land and therefore contaminates the wells from which people take water. And the more well you take from the water, and the more the land is exposed to saltwater intrusion. And therefore people started to be concerned because they found increased salinity in the wells. And once the soil is contaminated by salt, there is no way to recover it. And therefore they had to find alternative sources for water supply. And the solution was this dam. Now, keep in mind that adaptation has an impact, adaptation itself has an impact also on the CO2 emissions, because building a dam implies a lot of emissions. And also the impact is manifold. You have an impact on the landscape, you have an impact on the ecosystem, you have an impact on the river ecosystem, which is relevant, and there is, at the end of the story, an impact on groundwater, because if you decrease river flow, there is also a decreased replenishment of groundwater. And therefore, these impacts have to be carefully considered. Keep in mind that any action to either mitigate or adapt to climate change has an impact, and maybe a social impact, maybe an environmental impact, but of course, these downsides have to be carefully evaluated, okay? And as I said, there is no universal solution. So what we need to know is to be prepared on the solutions and to be able, on the specific context, to choose the most appropriate one. Very often, the most appropriate solution comes from the integration, from a well-designed integration of several measures. When you want to solve a problem and want to minimize the risk, you have to be, as you know, a plan A, a plan B, a plan C, a plan D. And in this case, it's a very nice way to have a B plan, means that it's a very nice way of saying that we need the integration of several solutions. In this way, we cover the different scales, and also in this way, we can dilute the impact in time. Because, you know, mitigation has a strong societal impact. A way to dilute it may be to combine mitigation with adaptation, because some mitigation strategies may have a strong impact now, but in 10 years from now, like renewable energy, in 10 years from now, may be much more interesting. Okay, now, from the discussion that I entertained up to now, it clearly emerges, it clearly comes out the importance of taking the right decision. And this is another challenging issue when you discuss climate change, how to decide what is the most appropriate strategy. We know that there is an important discussion at the international level. How should adaptation policies be planned and mitigation policies be planned? And therefore, I decided to spend a couple of words on decision-making. Keep in mind that decision-making is a very important piece, a disciplinary piece for solving the climate change problem. Decision-making also involves communication, as we mentioned before, and decision-making under uncertainty is even more complicated, but there are methods. There are methods to take uncertainty into account. and in a constructive way also, because taking uncertainty into account, as I said during the discussion, also means that you can take the worst situation into account, as well as the expectation. Okay. So a classical approach to decision making is the so-called top-down strategy. Top-down means that you start from a future climate scenario, and which is typically generated by climate models. And with this scenario or multiple scenario, you produce a design variable like extreme rainfall or extreme droughts. This design variable is typically routed through another model, mathematical model of the Earth system that is involved. Like if you are interested in floods, the climate model gives rainfall, and then rainfall is used as the input of a model that transforms rainfall into river flood. So there is a cascade of models through which we get a design variable, which are finally used to decide what is the best action. So if I have a flood problem and I decided to increase the height of a levee, how much should I increase it? We take, in the top-down approach, a climate scenario or multiple scenarios. If there is uncertainty, we know that several different models give different simulations, so we get all of them. We route them through a flood model, and then the flood model says you need a levee that is 2 meters higher. Okay. Before I move forward, let me open and close a parenthesis, and which I want to open to give you the feeling of how complex the problem is. What did we notice so far? Because building levees has been a strategy that humans used since probably since the Roman Empire, but even before that, even the Etrurians started to build levees along the rivers. And what did we notice recently? Because in the last 100 years, there has been a tremendous development, societal development, and consequently also, as we know, an increase of the pace of climate change. What did we notice? When you build a levee, or when you build a dam to cope with droughts, people feel like the problem is solved. People feel definitely more secure, and they invest. So while if the levee is low, people are a bit afraid and stay away from the river. If they see a very huge levee, they go straight against the river and invest money with the houses, with the companies, with the manufacturing, etc. And then if a flood comes that finally overtops the levee, the damage is much higher than in the absence of any adaptation. This is called the levee effect. It's a phenomenon that was known in Italy already in the 60s of the past century, when they raised the levees of the Po River. After the flood in 1951, they decided to raise the levees 1 meter. And suddenly they noticed that in the 60s and the 70s, they noticed an increase of the value of the surrounding areas, and they were a lot afraid because they said, we realized that a flooding of the Po River today would have an impact that is much higher than the impact that it had in 1951. So you see the complexity of the problem, and you see that we have the need to, in a way, to take into account, besides hazard, besides the likelihood of a flood, also additional variables like the value of the investment in the area that is hit by a disaster. Close the parenthesis. What is the problem of the top-down approach? The problem of the top-down approach is precisely uncertainty, because in a cascade of models, each of one is subjected to uncertainty. There is an amplification of uncertainty. If you use a cascade of models, there is an amplification of uncertainty. And what is the problem with the amplification of uncertainty? The problem is that if you want to make a precautionary design and you take the worst situation, then the project is too demanding in terms of resources and turns out to be not doable. And this is what always happens in climate policy, that we advocate for actions, but then when we go to the design of these actions, we realize that we don't have the resources. And the reason is precisely the presence of uncertainty, which forces us to take the worst prediction. Why this is a problem? Because the challenge remains unsolved. And what is even worse is that the challenge is already here. When we focus on climate change, when we look for solutions, it's because we had a disaster, we had people who died, we had a shock, which means that the problem is already here, which means that we need a solution now. And if we adopt an approach to decision-making that at the end of the story gives a solution that is not practical, we cannot put into practice, this is a huge problem. And this is why then people decided to look for an alternative to the top-down approach, an alternative to the so-called top-down approach. And what is then an alternative? Look, the top-down approach, it is very attractive because it's straightforward. It's very straightforward. It's easy to get a climate simulation. It's easy to get a transformation model. It's straightforward. And so this is a big advantage. The disadvantage is precisely then when you get the climate simulation and you consider uncertainty and you want to get the worst situation, then it's a problem. Okay, so what is the alternative? The alternative is what is now called the bottom-up approach. And look, the names correspond to communication strategy. We know that terms like grassroots approach, bottom-up approach means that we start from the people, we start from involving people. Top-down means a hierarchical decision, a decision that is dictated by the top. So indeed, this bottom-up approach, what does it do? First, I will give you some more details by illustrating two bottom-up approaches, but let me give you the basic principle. So the bottom-up approach starts from the assessment of current problems, current vulnerabilities. Did I have a flood? Okay, this is my problem. I am vulnerable to flood. Did I have a drought and the water supply system failed? Okay, this is my problem. I need more water. And this is something that it's not very easy to assess the vulnerabilities. After a shock, it is relatively easy because you had a shock, but so you had an example. But if you want to be in a way precautionary, act in advance, this is not easy because this is another problem with climate change. We tend to react only the day after a disaster. And then we rapidly forgot. There are studies on that the memory of disasters is very short. It's about 20 years. After 20 years that people didn't get any disaster, they assumed that the disaster was just a black swan and will not repeat into the future. So assessing current vulnerabilities is not easy. It's not as straightforward as getting a climate simulation. So we start from the current vulnerabilities and then we look for a solution. Even in this case, it's not easy. I got a flood. What is the best solution? a dam upstream retaining water, retaining excess water, or increasing the levee. I need to carefully assess whether the downside of one solution compared to the downside of the other solution, how they compare. Increasing the levee, as I said, has a downside, the dam has downside, so I need to identify strategies. The requirement, but we have in place solutions for that. So, I mean, the science gives us solutions in engineering, for instance, for evaluating the impact of dams, for evaluating what is the best solution. And then once we identify the best solution, then we call into play the climate scenarios to check to what extent the solution is durable in the future. So we make a climate prediction up to 2040. Is the solution still durable? Maybe for some simulation, yes, for other simulations, not. So how many simulations show a failure of the solution? 10%, okay. Let's take a risk of 10% that the solution is not durable. If the solution is not durable, let's introduce another question. Is it possible to update it? So if the levee is raised, is it possible in the future to raise it again? You know that there is a maximum height for levees. It's about 15 meters, Earth's levees. And above 15 meters, we don't go because it's too dangerous. If they fail, you get a cascade, a flood that is, I mean, too massive. So let's evaluate if the solution can be updated. And then if it can be updated, this is perfect. It means that, okay, some scenarios predict that the solution may fail. Let's wait 20 years. And if we need additional resources in 20 years from now, that's fine. If we don't have the resources now, it may be that in 20 years we can make a plan, we can make a plan for an accumulation plan of resources for updating it. So the scenarios are called into play with their uncertainty in a second stage. And then we end up with a solution which hopefully is no regret. Keep in mind this term because it's another important term. A solution is no regret when whatever it is, whatever the future, the solution is still useful. It's not a solution that if climate change increases is not useful at all. And a solution that may be prone to updating, and a solution that takes the most relevant source of uncertainty into account in the second stage, not in the first stage. So you avoid amplification of uncertainty through a modeling cascade. This is much more interesting. Of course, when you assess reality, you also have uncertainty when you assess vulnerability, but it's less than uncertainty of model simulations because it's based on assessment of reality. You may get information. This, I think I have a sketch here, which shows to you the top-down approach, starting from scenarios to design variables, vulnerability of system. And here we have two different bottom-up approaches. The first one starts from the evaluation of the possible strategies. So I have a problem. Let me start from the possible solutions. And then the solutions, for each solution, you estimate the vulnerability. And then you elaborate your strategies. And if needed, you come back. The other one, which is called decision scaling, starts from vulnerabilities, assessment of vulnerabilities, and then you don't see here, sorry. Let me just move this. Let me move here first, perfect. Starts from vulnerabilities. And then the future scenarios are used to assess the plausibility of this vulnerability with respect to future climate. And then you end up with a decision. You don't need to learn how these two methods are structured. There are no questions at exam about this. a question that you may expect at the exam is, what is climate change mitigation? What is adaptation? What is the difference between the two? And then you get closed answers. Or you may find a question, what is a bottom-up approach and what is a top-down approach? And what is the difference between the two approaches? And you see 5 possible answers and you have to select the best one. But you will not be asked to explain how robust decision-making or decision scaling work. These two methods, these are bottom-up methods, they have been compared, because if you start from strategies or start from vulnerabilities, you may end up with slightly different solutions. They have been compared. Let's say that there is no much difference in terms of results. What is different in these strategies is the communication with people. And so in some cases, you may want to start from evaluation of alternatives, assessment of candidate strategies. In some other cases, you may want to start with assessing vulnerabilities, and the solution comes later. It depends really on the problem at hand, and also it depends on the context with whom you are speaking. It depends. And of course, it's not the purpose of this course to go into the details of this, but I just wanted to give you some information on decision making, which is really relevant. Now, let me just say a few words on the future climatic scenarios, because in the top-down approach, they are the starting point. In the bottom-up approach, they are still used. They are an essential information. So we need prediction of future climate. So it's not only climate models that can produce climate scenarios, and this is important to say. And also keep in mind that sometimes you need weather scenarios, not only climate scenarios. What does this mean? Climate is statistics. Climate models typically, you assess their output in terms of statistics. You don't go to get the individual observation. So you don't get really the prediction of annual rainfall in 2050. You get statistics of it. And the way people prefer to focus on statistics, the reason is precisely the presence of uncertainty. Uncertainty in statistics is a bit reduced with respect to uncertainty of an individual observation. If you want to predict the rainfall or the wind speed for one day, it's much easier to predict an average of the wind speed that you may expect in January, rather than predicting for each day of January the individual wind speeds. So climate model usually, they produce actually simulations of weather, but they are evaluated in terms of statistics. But recently, there have been progresses in climate modeling. And these progresses means that there is a confidence that uncertainty is reduced. And therefore, there is an ongoing attempt to further reduce it. So there is an ongoing attempt of pushing climate models to produce weather. Weather means observations, individual observations of variables that are relevant, climatic variables. So it's not average rainfall. Weather is daily rainfall, it's hourly rainfall. There is an attempt, as I said, of pushing climate models to reproduce weather. So maybe that in the future, we can push climate model until to weather. And for instance, there is an active field of research that is trying to reproduce the convective processes. These are called convection permitting models. I'm not an expert, but I just read a couple of papers because I needed for a research project, I needed to know some more. And I find it is interesting because the lack of the uncertainty in reproducing the convection is still one of the major limitations of climate models in reproducing the weather variables. And as I said, the development are very promising. With the National Recovery Fund, there are research projects that are being financed for a significant amount of resources precisely on improving climate simulations. But at present, as for today, if we want to reproduce weather, we need to couple the climate models with what is called a weather generator. And how does it work? The weather generator takes the statistics from the climate model and generates the weather by combining statistics of the climate model, so predicted statistics, with historical statistics, statistics estimated by using historical data. And the weather generator is typically what is called a stochastic model, a complicated word. It's a statistical model, combining these two statistics, observations and predictions. For instance, I give you an example. I mentioned just during the discussion before, and by the way, thank you for giving the opportunity also to mention this, that climate models still suffer in, I think I mentioned it, in the reproduction of the multi-year droughts, which means long-term droughts, droughts that last for several years. And these events occurred in the past, so we can estimate the probability of these events by looking at past data and use climate model statistics in order to increase this probability of these events for the future in a way that we are not detailing now. I just want that you get that by combining the analysis of past data, which by themselves are not representative of the future, but are representative of essential weather statistics that climate model cannot still capture. By combining statistics of this historical observation with the statistics given by climate models, then we end up with a reliable, hopefully, representation of future weather. There is a question? Yes, please. I repeat. You can tell me and then I repeat for.
The climate models use the same data as the weather. I mean, what is the difference? Maybe one is local and one is global. We use for the climate models.
Typically, the climate models work at the global level, and they produce a global simulation, which is the scale is becoming finer and finer, but it is quite large in terms of space, like 10 kilometers, 10 kilometers, and therefore is not really representative of the point. And also there is one more thing, and then the weather generator operates at the local level, at the resolution that you wish. But there is one more thing, sorry, the question was, I forgot to repeat it. The question was, the climate model, doesn't it predict the weather by itself? So doesn't use the same data. So what is the difference? Maybe the scale? And I replied, yes, the scale is one difference, but there is one more thing that we should say. The climate models, when I said that there is uncertainty in the reproduction of some statistics, and I want to be clear, climate models are very good for temperature. When I talk about hazards, they are related to water, hydrological cycle, and it is known that in the reproduction of the hydrological cycle, there are a lot of uncertainties. And the climate models, they still fail also in reproducing the past climate in terms of hydrology. So when we compare for the past climate, I am writing a paper now because I am interested. You know that in Bologna, we have a time series of daily rainfall that goes back to 1813 up to today. It is an unbelievable source of information. And the climate models, we have the opportunity of reproducing the past observations up to, it is 1850. I'm looking at my student, 1850. 1850. Okay, 18, yeah. Okay, so they also give a reconstruction of the past data. And we are comparing with the student the reconstruction by several climate models and the observed data, and they still fail in reproducing the local rainfall, I mean. And of course, there is an open question, which is when you compare an aerial rainfall at the resolution of 10 kilometers with one point of measurement, which is very local, yeah, you should take into account that there is some difference, but still, they don't use the same data basically, because when you analyze the historical data, you see some features of climate which are relevant because they are already here. So you start from the bottom up and are not reproduced well by climate models. I hope I was clear. Okay. Now, there is one thing that I also want to mention about climate scenarios. And I anticipate my conclusion. Unfortunately, climate models may severely underestimate the future risk because they have a very limited capability of predicting tipping points. And this is really something that should be taken into account, meaning that the prediction of a climate model may be overly optimistic. What is a tipping point? Is a critical threshold. I really like this figure, which it was presented in a conference in 2020, in a virtual conference, because it was in May 2020. And this medalist showed this picture. I think it is really nice, and I asked permission to reproduce it, and I got it. So it is on my website, and because I got permission. So typically, when we look at an environmental process like climate, we start from a stationary condition, and then there is a perturbation which is a fast change. And the stationary condition is predictable and also is stable. When you go in a under change, it is conditionally stable, meaning that, okay, still the change is under control, everything is fine, but you may get, and our knowledge is too limited to predict that, to a critical threshold. And the critical threshold, if you pass it, the system may evolve in an unpredictable way. So maybe that the system evolves in a positive way, but maybe that it evolves in a very negative way. And given that we don't know what is governing these tipping points, we have a limited knowledge, we have some intuition. I will show another slide with some intuition, but we have a limited knowledge of what may happen. We have a limited knowledge of the potential of these thresholds. Of course, what we don't know is not reproduced by a model, because a model is a mathematical translation of what we know. If there is something that we don't know, the model doesn't predict it. So tipping points, who knows? And let me give you an example. If you look at sea level rise, starting from the pre-industrial period, there was an increase of 15 centimeters. And strange enough, this increase took place with a steady pace. So it didn't increase much after the start of global warming. The sea level kept increasing at a very similar pace. After global warming, you may notice, it depends on the location, because the sea level is not constant, by the way, but it is a constant pace, more or less, 15 centimeters, which is, one may say, not too much, actually. There are predictions by climate models, and up to 2100, and the worst of them give a prediction of about a further increase of 50 centimeters, the worst models, which start becoming something in a way concerning, but still manageable, because, you know, if it take place in 80 years, it's still manageable, 50 centimeters more. And because it's fast change, what is more concerning. But there are a lot of research projects now that are investigating the likelihood of an event that may happen, which is a sudden melting of the ice cap, especially the North ice cap. Why should we melt suddenly? Because we recently discovered, like 10 years ago, I don't remember, but you can easily see, but very recently we discovered that embedded into the ice cap, there are huge lakes, but really a huge amount of water, which is trapped there because the pressure given by the glaciers above basically is such that water doesn't solidify. So the question, it doesn't become solid. So the question is, what happens with the progressive melting of the glaciers above? Will this water become solid with a decrease of pressure, or will it remain liquid? And if it remains liquid, it may happen a sudden flood when the crust of ice is finally broken, because the water is under pressure. So what we might expect is that the water pushes against the ice, and it's balanced, this pressure is balanced by the weight of the ice. But it may happen that you decrease the thickness of the ice cap, and the water under pressure breaks it. And if it breaks it, this is a huge amount of water that may suddenly, in a very short period, be released into the oceans. And it may cause an increase of sudden increase. Sudden means maybe in 5 years, but still very, very rapid, of some meters. Is it likely? So these people with these research projects are doing two things. They are taking carrots, ice carrots, first of all, to quantify the amount of liquid water. They discovered several lakes with a volume that is impressive. The lakes that are much larger than the Italian lakes. There are several of them, and they are trying with the isotope, by analyzing the isotope composition of these perspectives, of these carrots, they are trying to understand whether in the past, when the ice cap melted, because you know in the past of the history of the Earth, you have learned that there were periods without ice caps. They are not a constant on the Earth. And they are trying to understand when they melted in the past, if the melting was sudden or not. But this is something that is currently not embedded into climate models and ocean models. So when they make these predictions, 50 more centimeters in 2100, they are not considering this eventuality, which is, I mean, something interesting. Some tipping elements of the Earth's climate system, and I think it is on Wikipedia. You can, if you look in Wikipedia for tipping points, Earth system, but tipping points, I think it's enough. You get this picture. And for instance, you know, you look at the Africa Sahara greening, you know that the Sahara was green. And then there was this tipping point which became, brought the Sahara to a desert condition. There is the dieback of forests. So boreal forests, we know, for instance, the Amazon, they are cutting it. And there is the feeling that if you go beyond a certain threshold of cutting, the entire forest may disappear, because the forest may be self-sustaining to some extent. And there are also, in ocean circulation, there is there are possible tipping points. Instability of the ice caps, it's mentioned there. And I also want to mention another example of tipping point. And if you, let me just open a new web page. If you look for, in Google, Lake Aral disaster, this is another interesting tipping point. And in Wikipedia. Let's here it is. There is a nice picture where this is the extension of the Lake Aral today. Not today really, because I think the date is let me see, 2014, and it's 2014, 1989. The Aral Sea was one of the largest internal lakes of the Earth, and it disappeared. And what you see here now, this white color is salt. So this land is a desert. There are interesting pictures I will show you. Why did this happen? The main reason was the diverting rivers. The Russian economy was based on cotton, especially at that time, and they diverted rivers for irrigating the cotton. And what happens was that by diverting the river, the lake started to shrink. Shrinking the lake caused a reduction of evaporation and therefore a decrease of rainfall, a local decrease of rainfall. And this is an example of local, if you want, man-induced climate change, anthropic and human-induced climate change. And it is irreversible because now there is no evaporation. And this is a tipping point. There was a threshold of evaporation, below which the weather, the climate changed definitely in an irreversible way. And there is no way to go back now. Even if you put again the rivers into the lake, there is no way. And this is a nice example of a tipping point. There is a similar problem if you search for, sorry, I just want to show you some more pictures. Here there are some, you see, there are, it's a desert now. There are both that are left into the land. The land is salted. Vegetation is practically zero. And another interesting example, it's Lake Urmia. It's still, let's hope that we can still recover it. And here the lake is shrinking. Let me see if there is a nice picture. Anyway, I don't want to, I leave you to getting information. Here, it's a problem that is being analyzed, assessed, and hopefully there is still time to avoid crossing a tipping point, but the lake is shrinking with a considerable pace for similar reasons, climate change plus land use change, human drivers combined, which caused this. I think I can now make the break. I go back to this figure and I think we can make a 15 minutes break. Any questions so far? Thanks. See you in 15 minutes from now. I stop the video and the audio. Okay, I think we can restart. Let me check. There is a message in the chat. Okay, thank you. I see some references. Very good. Okay, so this slide, I already discussed the content, and I just want to take this opportunity to mention that in the list of the lectures that you find on my website, you find a lecture that we didn't discuss, which is dedicated to climate change and water cycle. It is a lecture that took, it's already 3 years old, I think, but it is continuously updated, and it took a lot of time to being put together, and if you're interested, it's not technical. If you're interested, I suggest that you have a look. There are several graphs, and it is discussing what is the state of the art in historical data analysis and regarding water-related variables like rainfall, like droughts, like flooding, and it's providing also an overview of climate simulations and the current state of the art of climate models. And you see the last bulleted item, conclusion bottom up. Basically, it is the conclusion that I want to make regarding decision making. It's decision making, the modern decision making is based on the bottom up approach, which means starting from people and starting from data, and taking into account, of course, the knowledge, the simulation by climate models, and the knowledge gained so far, and also the knowledge of the related uncertainties. And again, I would like to say that uncertainty is not a problem if we know it. If we know, for an engineer, this is a classical say. Engineers are used to deal with uncertainty, and therefore we extend it by saying uncertainty is not a problem. If we know it, it's not really a problem. And it is a problem when you don't know it. When we don't know uncertainty, it is indeed a problem, because whatever decision we take, it may fail. Okay, and let me now move forward to a topic which is, I think, interesting, because it allows us to set the basis for climate change adaptation, and to clarify that changes in climate are not only the required information to successful mitigation and adaptation. And the essence of this final part of this course is to clarify that climate change mitigation and adaptation should be designed basing on a comprehensive assessment of climate, including climate change, and society. So it is a comprehensive assessment of the topic, which gives us the basis for a successful strategy. And I want to give 2 examples. We clearly noticed, and this is a concept that is new, is being developed now, we clearly noticed that in some cases, even a small change in climate generates a strong impact. In some other cases, it may happen that changes in climate generate a less impactful situation. And the fact that changes sometimes generate a much stronger impact, we can term this as risk amplification. It is a particularly concerning situation because it leads to extraordinary events like those that are called mega floods or mega droughts. For instance, the flood in Germany, in Central Europe in 2021, this has been a mega flood. And if you look at the observations of rainfall, I mean, it was an extreme event, but not as extraordinary in terms of rainfall as the impact. The impact was extraordinary. The extreme rainfall, I mean, was extraordinary, but not as much, which means that there has been an amplification of the impact, an amplification of the risk. And this phenomena of risk amplification is those who generate events that take communities by surprise. And the flood in Central Europe of 2021 is an excellent example. People and managers, administrations were not expecting it. And the management of the flood turned out to be poor because when something happens that we are not expecting, the management is problematic. And our current understanding suggests that risk amplification is generated by climate change, plus some more, plus some critical conditions in what? In ecology, for instance, in water cycle, it's the hydrology behind it, which is already critical, is close to a tipping point. So a small change in climate generates a tremendous impact. Plus society, because it's the societal organization also that may have an influence. And therefore we are identifying this challenge, how to recognize these situations in advance, how to be able to better predict these situations so that we can anticipate these mega floods, these mega droughts, these events that are also called black swans. There is black swans to mean something that is very rare. And there is a book written in 2007, which is called Black Swans, which describes these events that take humans by surprise. And then to better understand what are the mechanisms that can lead to this amplification, let's discuss briefly this topic, risk-based adaptation design, which allows us to get an introduction to understand how these mechanisms can work. So let's start by saying that we focus on risk, and let's define what is the risk. I used this term at the beginning of this lecture, and we use the term very frequently, but it is often misused. And let's define from the point of view, from a technical point of view, what is risk. The risk induced by a considered event, so risk of flood, risk of droughts, risk of whatever. And it's given by the combination of three factors, of three multiplying factors, which are the hazard, which I already introduced. It's the probability, the likelihood of the event. And the other two factors are exposure, E, and vulnerability, V. So what is the risk in practical terms? I said that it is determined by a combination of these three factors: hazard, exposure, and vulnerability. But in practical terms, what is the risk? It's the measure of the expected damage that is caused by an event. And let's get into the details of these three factors to better understand. So there is hazard P. So let's say it's the probability, the likelihood. Let's forget about what is a definition of probability. I think you have in your mind an understanding of what is, because it's part of our current language. It's probable. Tomorrow is likely that it will rain. The probability of rain is high, or the probability of a given party to win the election is high. It's part of our, it means that an event, a considered event, is likely or not, probability. Okay. And this is the hazard. What is the vulnerability? The vulnerability is, again, a probability, but not a probability of occurrence. It's the probability that the system, for instance, a given community of people, is damaged at a certain level if the event occurs. So let me try to be clearer. If a town is protected by levees, even if an extreme river flow, an extreme flood comes, there is a reduced probability that the community is impacted because there is the levee. If I remove the levee, the community becomes more vulnerable, meaning that the event comes and it's highly likely that the town is inundated. So vulnerability takes into account the protections, the levees, the dams, the existing dams, the significance of the water resources. Good. What is exposure? It is the value, the economic, if you want, value, but it may be a value that goes beyond money. It is the value of the assets that are exposed. So let's reflect on the combination of these three factors. It may be that a flood comes with no protection, high vulnerability. A flood comes, high vulnerability, but nothing is there. The risk is zero because the exposure is zero. If nothing is there and there is not any environmental value, because sometimes damage, economic value, is not only related to people, it may be related to a natural environment, which is highly rewarding, it's highly valuable. But if nothing is there, risk is zero, because even if the flood comes, even if the land is vulnerable, there is nothing. Sometimes we get floods and we don't even notice that. Or in the past, sometimes people were not concerned by floods. Why? Because nobody was there. So this is also why sometimes we don't have records of past floods. Because when they occurred, nobody was hit and nobody knew. Okay. Another example, you may have a very high valuable land. A flood comes, but the land is completely protected. And therefore the risk is zero, because it's impossible that the protection fails. Okay, very good. It means that vulnerability is zero. It is one of the factors of this product. You see, below here, risk is equal to the product of hazard. It is indicated with P here because it stands for periculosity. Sorry for that. But let's take that P means hazard, vulnerability, exposure. If vulnerability is zero, risk is zero. If exposure is zero, risk is zero. If likelihood of the event, hazard, is zero, risk is zero. And typically, this is a probability. So it's in the range 0, 1, because this is something that I am saying about probability. Probability is expressed with a number between 0 and 1. So P is between 0 and 1. Vulnerability, we define it as a probability, which means that it's again between 0 and 1. E is an economic value. So it's expressed in a dimensional form. It may be euros, it may be dollars, it may be something different, not necessarily money. So it means that if you get a flood and the area is vulnerable, it's totally inundated, E is the value of the area. If you reduce vulnerability and reduce hazard, then the risk in the same unit as E decreases. So the risk is expressed in units like E, maybe euros, but again, not necessarily money. It may be a value that you quantify in different units, like environmental value. Can you really translate it to money? Sometimes not. Another topic which I am very keen on, cultural heritage. Sometimes you have cultural heritage exposed to flood and droughts and climate change. This is a topical research issue today. Climate change and cultural heritage. The damage that is caused by climate change on the monuments, on the churches, on the cultural heritage in general, which may be also intangible, like traditions. These are all issues that are impacted by extreme events. And the value is sometimes expressed in different units, because especially for cultural heritage, it is sometimes it's impossible to translate it in economic terms, okay? So risk again is the same unit of E. And let's now dedicate the remaining time to the assessment of the effect of climate change on hazard, vulnerability, and exposure. And you can already get that what is probably most sensitive to climate change is hazard, because it changes the probability of occurrence of the event. Let's try to investigate some more through a graph. And this graph is my invention. So if you want to blame someone, it's me. If you don't understand the meaning, this is me. And don't assume that you understand it quickly. We need some reflections on that. And let me explain what is in the axis. So first of all, in the vertical axis, you have the three things: exposure, vulnerability, and risk. And you know that risk is the product of exposures by times vulnerability times what? Times hazard. And the hazard is reported here on the horizontal axis. It is called here intensity of the event. Why? Because likelihood of an event is directly proportional to its intensity. They are the same thing. There is a one-to-one correspondence, meaning that an event that is more exceptional, more intense, is less likely, is less hazardous, okay? And this is something that you may have some difficulties in understanding, because you may say, but if an event is exceptional, how can it be less hazardous? Remember, hazard means probability. Is an extreme flood, a mega flood, likely? No, it's not likely. It's something exceptional. It doesn't happen every year. And therefore, it means that the likelihood is lower, and by definition, the hazard is lower. Okay? But if the event is more hazardous, what do we expect? That vulnerability with respect to that event changes. The system becomes more vulnerable to that event. If a flood occurs every year, the system is not vulnerable because people got used to it and they adapted. If an event happens once every 1,000 years on average, under climate change, it may happen more frequently, then people are not expecting it, they are more vulnerable. So when the intensity of the event increases, look, this axis means high hazard, lower hazard. But lower hazard means that the event is more intensive. And therefore vulnerability, which is the red curve, it is expected to increase. And look, vulnerability is expected typically to be 0 up to a certain level because people are prepared to it. To the floods that occur every year on average, people are prepared. So vulnerability typically is 0. But then if you increase the intensity of the event, vulnerability increases. And the red line is just a guess. Is something that is meant to represent what I said, that vulnerability for an event that is highly likely is 0. For an event that becomes more unlikely, starts increasing, and typically it keeps increasing. Okay. What about exposure then? Okay, so let's take into account that if an event is small, not intensive, the affected community has a lower size. Or let's imagine that you get a flood. First, if the flood is not extreme, the inundated area is smaller, and the depth of the water is small. So the exposure, it's not really much because water doesn't reach the first floor, for instance. Or about cultural heritage, usually when there is a risk of flood, if you go into the churches, you see that the paintings are not at a low position, they are put up. Because like in Florence, if you go in Florence, after the flood of 1966, they moved all the paintings 1 meter up. It means that the exposure, if the flood is not intensive, it's lower. Once that the floods keep increasing, the extension of the area and the depth of the water increases, and you have the exposure that is increasing. After a while, we can imagine that you get an exposure that is flat, because everything is inundated and it's flat. This is just a guess, but I mean, depending on the context, you can draw this graph through an assessment, and we can be, we can reach a fair amount of detail, a good detail, because this is based on an assessment of the current conditions. It is possible. And then what about the product? Remember, the yellow curve. Until vulnerability is 0, the risk is 0. When you increase the intensity of the event, you get that the likelihood hazard decreases, but you have an increase of vulnerability and exposure, and the product of the three typically gives rise to an increase of the risk up to a max. Typically, the risk curve reaches a max because after a certain intensity of the event, vulnerability stabilizes, exposure stabilizes, and if you keep increasing the intensity, you have the likelihood, the hazard decreasing, and therefore the risk decreases. So what is the reality? The reality is that sometimes, not always, but in typical context, if the event has an exceptional magnitude, it is so unlikely that is not representing the highest risk. The highest risk may be represented by an event that may occur every 50 or 100 years on average, which causes the highest risk because the combination of hazard, probability, and exposure and vulnerability is the worst possible one. And this is what I meant to say when I said risk amplification. We have to understand these situations where there is something that is still possible with a moderate frequency and represent really a high risk. Something that is almost impossible is not a very high risk, usually. Understanding this picture is at the core of the design of adaptation. Let me give you an example. I mentioned Florence. Florence was flooded in 1966. It was something really unexpected, and the damage was huge. 35 people died, and the damage, if you look at the pictures, there are a lot of publications. I also contributed to a publication on the reconstruction of this flood, and it is really amazing if you read what happened. It was something really unexpected. And the damage in terms of also damaged cultural heritage, but I mean, the inundation was really a disaster. So after the flood, what did people do to solve the problem? In a word, nothing. Florence is in the same situation. The only thing that was done was to lower the aprons of the bridges. Aprons means the foundation of the bridges. They lowered it a little bit. So basically they increased the conveyance of the river, the capacity of the river to bring water out of Florence. They increased it about, I think, 10%, which is nothing. Because the flood was like 3,000 cubic meters per second of water. 3,000 cubic meters of water per second was very huge. And the conveyance was, the flood was, I think it was like 3,400, and the conveyance was about 2,800. But keep in mind that once you exceed the conveyance of the river, everything gets flooded. And so even if you pass of just a small amount, it doesn't make a big difference with respect to passing 1 meter of water level over the levees. So basically, they tried to increase the conveyance 10%, which brought them to conclude that probably in the current situation, the same flood would not cause any flood. The same flood would not cause any inundation. But actually, after that, there has been climate change, urbanization. So Florence is in the same situation. It's exposed at the same risk. And it's a flood that has probably a frequency of expected frequency of once every 50, 100 years. It was not really exceptional. And so 56 years passed, and pessimist people like me say that Florence is going to be flooded again, unless we do something. Actually, they are now introducing some more measures, but still, I would say that, not only me, I would say that the result of the assessment is that the likelihood of a flood is still very relevant. And this is what I mean when I say that sometimes we don't do anything because adaptation is refused, or the prediction of climate models highlight a situation that it's impossible to solve. And I think this is really an example where the bottom-up approach should be adopted. Let's solve the current problem. Now Florence is exposed, let's solve it. At least by increasing the conveyance of the river of a significant amount. But it is not easy also because, you know, if you increase the conveyance of the river in Florence, it's still an ongoing discussion. What does this mean? That you are bringing more water downstream and you may flood Scandicci, which is a downstream town. And of course, you know, on the other hand, you cannot use Florence as a flood basin in order to save Scandicci. We should, I mean, find a solution that it's a good compromise. Not easy, but this kind of assessment may help. This is the explanation of the graph, this slide. So I think we don't need to spend more words on that. I just would like to say, let me go back. Climate change is acting here in the intensity, or better, it's acting in the hazard associated with the intensity of the event. And therefore, here there is hazard associated to intensity. I said that there is a one-to-one relationship. This one-to-one relationship may change after climate change. And therefore, the shape of the resulting graph may change. Okay, now, I would say that according to the bottom-up approach, we can conclude this part on risk-based adaptation design by articulating the design itself in two phases. In the first phase, we assess the effectiveness in terms of vulnerability and exposure of the adaptation solution by referring, for instance, to the current curve. And in a second phase, we analyze the impact of climate change on the hazard. And we see, after climate change, what is the effectiveness of the solution. And of course, this may bring to an indication of its resilience against climate change. And what is the advantage here? The advantage is that at least we find a temporary solution, at least we find a solution to current problems. For Florence, at least we would improve the situation. Okay, now, let me just give you an example of adaptation solutions. And this is very descriptive. And first of all, a premise on the principles. This is a list that is repeated on the website. So let's keep into account that the effect of climate change vary by region. And also the output of climate model is different. If you look at different regions, there are, for instance, we talked about this, global warming is higher in the pole, in the North Pole, and is higher in the mountain regions. So for reasons that are not yet completely understood, it is called polar amplification. It's the subject of ongoing research. The effect of climate change may vary across demographic groups. And also, you know, this is important to be taken into account. I spoke with some colleagues from Iran, and they say that the effect of climate change in Iran is more pronounced because in Europe, you know, the climate gives us some more flexibility, some more opportunities to adapt. You know, in Europe, fortunately, we have plenty of water. And also our vulnerability with respect to floods and droughts is reduced. Of course, if you have more resources available, vulnerability is reduced because you can adapt. To adaptation need resources. Let's also consider that climate change poses both risks and opportunities, like any disaster, like any, unfortunately, any human contrast. For instance, I give you two examples. The pandemics brought the opportunities, and we stated that to honor the memory of the people who lost their lives, we should make an effort to profit from the opportunities that the pandemics offered. This is why also I am discussing with the governance of the university what are the advances that we made with remote teaching, with the virtual teaching, and with the use of technologies in teaching. And these steps forward should be kept. Of course, it's not easy to, it depends on the disciplines, it depends on the degree programs, but another example is the First World War and also the Second World War. They promoted an advance in technology that was massive. The First World War brought an improvement in airplanes, in aerodynamics, in technology in general that was massively significant. And the same thing for the Second World War. There was a big technological improvement. This is to say that from even the worst disaster, there are opportunities, and we have a kind of duty to profit from them. And the effects of climate change must be considered in the context of multiple stressors and factors. This slide is a kind of conclusions also of this course, okay? Just some final considerations. And adaptation comes at a cost, and also mitigation. It's unfortunately, if it was not costly, it wouldn't be a problem. And also, if you look at the renewable energy, the price of electricity started to increase already 2 years ago because of the investments that we had to make on the renewable, which is justified. But this implies that the cost is a social cost. It's a cost that sometimes for certain communities is unsustainable. And especially for those communities who have less resources. And in devising mitigation and adaptation, we should leave no one behind. Problematic. And adaptive responses vary in effectiveness, as demonstrated by current efforts to cope with climate variability. And it's the systemic nature of climate impacts. What does it mean, systemic? It means that there are climate impacts are acting on a different component of the human system. So I mentioned the fact that even if you build a dam, it's an adaptation policy, but it generates CO2 emissions and it generates an environmental impact. And it makes the problem more complicated. And maladaptation or malmitigation are to be absolutely avoided, because given that they require resources, we should use the resources in the best way. And also, when many opportunities for adaptation make sense, no matter climate change. So why should we be concerned by adapting Florence to flood? Because even if climate change was not a concern, this is a current problem that we should solve. Of course, we know why it is a concerning, why people are concerned, because they are costly, interventions are costly. And I would give another example to you. One possible solution for solving the Florence problem is to impound floods in retention basins upstream, which means that you take a portion of land that is close to the river and you don't use it. You just say, this is area that in case of a flood, I use to store water. Of course, if during the flood you store water upstream, you reduce the intensity of the flood downstream. This is reducing vulnerability. But people oppose to it. They oppose to it because they are the owners of these areas and they are not willing to be given a low amount of money in order to transfer the area, to give the area to the central administration for keeping the area reserved for impounding floods. And therefore, this solution turned out to be impossible for the strong opposition. Another opportunity would be, and it has been tried in Florence, to increase preparedness of people. If you increase preparedness to a flood, you reduce exposure. Because if people are used like to bring the values at the second floor, like it was used in the past, it was very, very frequent in the past. People living close to rivers, they were used as soon as they got some signal that a flood could come to bring everything upstairs. And in this way, you reduce the exposure. And therefore, the administration, the municipality of Florence, published a map of the area that could be flooded with increasing intensity of the flood in order to prepare people. And the map was published for, I don't know, but very short time. They had to withdraw it because people protested, because the value of the houses was impacted by this map. Because of course, if a house is is known that is likely to be inundated, the price goes down. I just want to emphasize what are the difficulties. This is really a multidisciplinary problem. And let's now give some examples of adaptation. They can be grouped into three categories: structural and physical adaptation. And this can be grouped into engineering and built environment, structural and physical adaptation, and then social adaptation, and then institutional adaptation, economics, laws and regulation, government policies and programs. Social adaptation includes education, information, and change of behaviors. And the structural and physical adaptation, I forgot to complete the list: engineering solutions and technological solutions, ecosystem-based solutions, services, etc. And structural and physical adaptation may include flood and drought adaptation, agricultural adaptation, including irrigation, for instance, or energy production adaptation. Social adaptation may include enhancing adaptive capacity, reducing poverty. Insurances, this is frequently used today, increasingly used. So sometimes it's better to take an insurance to reduce exposure rather than spending a lot of money to decrease vulnerability or to reduce the hazard. And then institutional adaptation includes effective policies or development of adaptation plans. Let me give some more examples of adaptation actions and more technical examples, more specific. So installing protective or resilient technologies in properties that are prone to flooding. Some people install waterproof doors and windows. And this is an increasingly used solution. If we are successful in keeping the water out of the houses, of course, this is a solution that could be effective in some ways. Keep into account that water puts a lot of pressure. Water is heavy, and when the water column increases in depth, it pushes a lot against obstacles. This is why people in the past used the opposite solution. When they saw that the flood was coming, they opened everything because they wanted to avoid that the houses were demolished by the flood coming. So these solutions must be carefully studied from an engineering point of view, but they are increasingly used. Or changing to heat-tolerant tree varieties, which means this is a protection against hot waves. We didn't speak much during this course of hot waves. We mentioned fires, but also hot waves are indeed becoming a relevant concern today, because there is also the combination of the heat island effect in the cities. In the cities, the temperature is increased much more than 1.2 degrees. It's increased in some cities also 3 degrees during, if you just look at the summer temperature, in some cities, also in Italy, it increased about 3 degrees, which is a lot. Again, also for the health of people is a lot. And then people turn on the air conditioning, which means energy CO2 emissions. It's a negative feedback. Rainwater storage, this is increasingly used as an adaptation option, which means that instead of releasing rainwater into the sewer system, which is also a risk because it implies a risk of flooding, a risk of urban flooding. Urban flooding in general is not very dangerous in terms of life of people, but it is very costly. And also in some cases it's dangerous, but it's less dangerous than river flooding. And then instead of releasing the rainwater into the sewer systems, if we accumulate it, and then we use it for some services inside the house or for irrigation, this is useful, effective adaptation options, reducing paved areas to deal with heat waves, hot waves, and to favor infiltration, to not to overload the sewer system, and also to favor the recharge of groundwater systems. Adding green roofs, this is increasingly used. I mean, the green roof is it's very interesting for many reasons. Keep in mind that in Italy, it is a bit problematic because in the cities, there are protected buildings, protected from the point of view of the cultural heritage. They are protected by the Ministry of Cultural Heritage, and therefore you cannot convert the roofs to a green solution because the buildings, when are protected, you can't touch them. They have to be kept in the original form, which it's fine. And also there is to say that in Italy, for the climate of Italy, with that high thermal excursion between winter and summer, if the roof is horizontal, it's a problem. And it is very likely that it gets damaged and gives leakages. This is a very likely situations, and the technology still it's a little bit behind to solve this problem. So the horizontal roof is fine when there is no high excursion between winter and summer, and for places where you have less rainfall. So you find it in dry areas typically, but you may also find it in mountain areas, like if you go in the Alps, there are a lot of green roofs because the thermal excursion between winter and summer is not so high. You know, it's a very high stress. For instance, here you have over a roof. In the summer, you easily get 50 degrees of temperature over a roof. If you tried to go over a roof during a sunny day of August, you realize that you don't resist much there. And during the winter, you can go to -20. So it's really a big excursion, which poses a great stress to the structure of the roof. This is why here we are remaking the roof isolation frequently. And requiring waterfront properties to have higher, to have more solid foundations. Because you know, the flood is also, as I said, putting pressures on the buildings, and therefore you need more solid foundations. And using pumps at wastewater treatment plants, because in this way we are increasing the capacity of these water treatment plants, which means that we can reuse the water. And water reuse is today a very frequent solution. In Europe, it's not possible to use treated water for drinking, but in some arid places in the Middle East, they are already doing that. They treat the water from the sewer system and get drinking water from that. There are technologies now, and some experiments have been made also to make a fully circular building in terms of water reuse, which means that no water is lost, no water goes into the sewer system. The water is completely recycled. These are interesting experiments, and also raising public awareness, surveying local vulnerabilities, understanding risk amplification, making climate change specific planning tools like flood maps. This is another adaptation option. Incentivizing lighter colored roof to reduce the heat island effect. Incentivizing the use of the roof surface to produce solar energy. It's not mentioned here. Buying out homeowners in flood-prone areas. This is another interesting solution. So in some cases, it's just much better to leave the flood-prone areas or change for coping with drought, change the crops, adopt less water-demanding crops, raising street level to prevent flooding. These are examples. Conclusions. Conclusions of the lecture today, and then a few words of conclusion of the lectures. Design of adaptation actions is a typical task of engineering, and as such relies on the prediction of future conditions. And traditional engineering practices are based on data analysis and modeling to infer the expected behaviors of the analyzed processes. And let's use them complementary. This is typical in engineering. Models and data analysis are used in a complementary way. Let's try to do the same with climate change. It implies some difficult problems, and a relevant problem is the dialogue between different scientific disciplines. We all recognize the value of interdisciplinarity, but putting interdisciplinarity into practice is difficult. And also, let's focus on the meaning of uncertainty. A comprehensive assessment of uncertainty requires, as it is stated here, a comparison of the predicted of observed data of the analyzed system. And it means that we shouldn't be afraid of comparing the output from climate models with historical data, because this is the target. We should get the models able to reproduce the historical data, and then models are ready to be used standalone for the future. And then we don't need any more integration between different models. The one that keeps, estimate the statistics of the historical data and the climate models. Once that we can target a unique model, but this model should be able to reproduce the past. It's not easy, but this is the way forward. And let me say, I think I can share the screen now, because if I'm not wrong, there is, okay, I think I can just leave on the screen this one for you to read. Let me check if it's finished. Yes, but actually I have the conclusion for the course that is given in another slide. So let me move to this one. So take-home messages. Let's first start from a premise. The climate system, we still have much to know about it. And this implies that we need more science, and the research is absolutely underway. It's not concluded, we know that. And it is extremely important that we promote climate research in order to reduce the uncertainties that we still have. Deductive and inductive models can be used together. We shouldn't be afraid of integrating models. To reach the target of a comprehensive and unique model, we need this integration, merging disciplinary expertises. And data show the key role, the important role of natural variability and human influence. And so it is extremely important that we try to inspect what is the interaction, the interplay, because we know there is natural variability. We dedicated one specific lecture in this course to try to understand it. And it is necessary to understand, because natural variability can combine in a negative way with climate. And we should be able to understand when there is this risk amplification that I mentioned. And there is the urgent need of adaptation, no matter the causes of climate change. So, and adaptation and mitigation needs to be coupled for the sake of building timely and durable resilience and sustainability. Let me say, okay, uncertainty assessment is a key information. I forgot that I had this slide also. Sustainability requires identification of no-regret solutions. We discussed it. And climate change assessment, mitigation, and adaptation is a rapidly evolving field. So it is necessary that you stay updated. It's necessary, as I said, to invest in research, but it's necessary also that you stay updated. And let me say that for what concerns my lectures, I will keep them updated, at least until I am teaching this course. Next year, I will be teaching this course again, and also the colleagues. And I will make an effort to keep my lectures updated. And with respect to the last year, I made several changes. And so these lectures are public. You can refer to them in the future. And finally, let me give you a kind of concluding remark. And the concluding remark is, let's look at climate change, and let's look at the many problems that it's originating with a forward-looking attitude. And I mean, we should be positive about it. We have the means to solve the problem. We have the means to mitigate it. We have the means to adapt to it. But in order to be successful, we need peace. We need a global cooperation. We need something that humans were never able to do until now, to cooperate globally. Is this possible? I don't know. I had a discussion yesterday with a colleague, and he asked me, do you think it's possible? Because if humans were never able to do that in thousands of years, it may imply that this is impossible. I don't know, but I think we have to be positive and find a way to give our contribution. And our contribution, should be a message that is very inclusive. And this is really hard, because when you are faced with facts like the recent war in Ukraine, it's really difficult to try to be inclusive and positive about the development, but this is my ambition, my aspiration, that in analyzing this problem, we can reach a global agreement which cannot be imposed from the top. It has to become from the bottom. And this is the way in which I really would like to send a positive message. Let's hope that for fundamental issues, we can really inaugurate a new era. And I think the keywords for this are equality, diversity, and inclusivity. You know, EDI, the EDI acronym is what is emerging now. And it's a concept that all of us agree with, but when we go to the facts, I think a few communities only were able to be very proactive in that up to now. And this is, I think, the positive attitude that we should take. So let's focus on equality, diversity, inclusivity. Let's leave no one behind. And if we are effective in discussing in this way, I think we can be positive. I want to thank you because this course is the second year that I'm teaching it, and I felt like it was an interesting experience for me. It is the first year, it was last year, the first time that I taught to an interdisciplinary audience. And if you ask my colleagues, the impression and the feeling that I reported back is that this is an experience that any teacher should make, because it was really interesting and challenging to try to change my teaching attitude in order to meet the expectation of interdisciplinary and international audience. It's not easy, but it's nice. Thanks. Serena, direi che è Giulia. Sono a posto. Aspettate che interrompo la condivisione e la registrazione.
Ok.